Hello everybody, welcome to today's COSI seminar. We have Matthew Reynolds, our guest speaker today. He's an advanced COSI student. Matthew received his bachelor's degree from the University of Colorado in geological sciences, and his master's degree from the Department of Applied Math here in CU also. And he's also working now in applied math in Gregory Birkin group towards his PhD. And guess what? His interest resided in the nonlinear approximation and methods of inverse problems. So
antennas.
And antennas.
Yeah.
Tennis. So thank you for volunteering.
All right. or being volunteered, or.
Yeah.
All right. Well, thank you everybody for coming. It's good to see so many people back from spring break so soon. If I weren't giving a talk, I might be still on a beach somewhere. But so anyways, today we're going to talk a little bit about nonlinear approximations. So in particular, we're going to talk about the kinds of nonlinear approximations that we use in Dr. Belkin's group. Here's the outline of the talk. I'm going to briefly go over linear and nonlinear approximations and speak a little bit about, well, why should we use nonlinear approximations when we're so comfortable with the linear stuff that we all learned undergrad and so on. I'm going to go into details on a couple methods of nonlinear approximation that we use. This talk is by no means inclusive of all forms of nonlinear approximation. And then the last part, I'm going to talk about applying these methods of nonlinear approximation to Fourier data on the disk and show a couple of examples. So if there are any questions or anything, please feel free to stop me as I'm going. If I'm going too fast or anything like that, just let me know. Okay. So when I say linear approximations, I'm talking about linear approximations in function spaces that use fixed functions or bases. And most of the time, these approximations are formed through linear combinations of basis functions. And a couple of examples of these are approximating a function with B-splines and approximating something with Fourier series. Okay, so the nonlinear approximations that I'm going to introduce in this talk, they do it a little differently. So what we're going to do is we take, instead of a basis set of functions, we're going to take a larger set of functions and we're going to select functions from that to make our approximation. So a couple examples of these larger sets of functions are exponentials with complex valued exponents and rational functions. And both of these approximations, we're going to select these functions from a wide set of functions, something that's much wider than a basis set, and we're going to form linear combinations of these. So it's similar to Fourier type methods in that manner, but when we're finding these functions, the way we do it for nonlinear approximations with complex valued exponents and rational functions is we use the SVD and then we use a root finding step after that. Okay, but we need to ask a question first. So why should we use nonlinear approximations? Well, the nonlinear approximations that we talk about, they're very efficient, so it's not subject to the Nyquist criterion. So we can make approximations that are very short as compared to standard linear approximations, and there'll be some examples in the talk to show you guys this. Error decays exponentially with the number of terms in the approximation. So this kind of goes hand in hand with the first one, in that the more terms we add, the error decreases significantly. These methods are also very good at extrapolation, and this is kind of a key for what we do when we approximate with rational functions is extrapolating data that we have in the Fourier domain. And tied in with extrapolation is the ability to mitigate the Gibbs phenomena without the use of windows or filtering. And we'll show some examples that show this. But I'd like to talk a little bit about an example first, kind of get our feet wet. Let's talk about Fourier analysis for a second and approximating a boxcar function.
What is the Gibbs phenomena?
The Gibbs phenomena. So if you have a function that has, let's just say, has a singularity, something like a step function, and you approximate it with a Fourier series. If you truncate the Fourier series too soon, you start seeing oscillations near that edge. And the problem is that you typically need a lot of coefficients in order to approximate without while squishing down these oscillations. So actually this is what this example is about. So here we just have a nice basic boxcar function, and you take the Fourier transform and it decays as 1 over c. And the bottom line is, well, this isn't band limited, right? So if you want to, say, approximate this with a Fourier series, you need a lot of basis functions, right? I mean, that pretty much makes sense. And, well, it's natural to want to say, okay, well, let's just choose someplace and cut it off. Well, the truncation does produce the Gibbs phenomena, which I just explained to Ariel. Yes?
When you say accurately and error, what kind of measures do you use? Points-wise or something?
So that's a good question. We're talking about error in a norm that it's better than it's in a norm that's better than L2, but it's not as good as L infinity type norms. So it's one of those norms that's in between those two. So you can kind of think of it right now as for L infinity norm, except for, if you have singular points that really shoot up high. So, okay, we can accurately approximate something like this with a short linear combination of rational functions. So when I say short, I'd say something on the order of, I don't know, 30 to 40 can give us a reasonably good L infinity type error. And this approximation in particular lets us, the reason that we can do this is this type of approximation, it allows us to extrapolate in the Fourier domain. Now, if you think about it, you typically, if you have Fourier data that hasn't decayed and you want to approximate something with a Fourier series, you're going to apply a window, something like that. Whereas this method extrapolates and therefore takes the data to 0 as you extend the support of your Fourier data much less harshly than if you just either cut it off or did something like a Kaiser window. So I'm going to show another example of that here in a second. All right, but for now, let's start talking about nonlinear approximations via linear combination of exponentials. So this was first introduced by Belkin and Monzon in 2005, and what they're doing is they're considering approximating a function on the real line in a finite interval with linear combination of exponentials with complex varied exponents, and the input data are samples of the function on an interval. So here's how we formulate it. So if we have f of x is smooth on 0 to 1 and we're given an accuracy and an interval size, we want to find complex weights, complex nodes, and a minimal number such that we can construct an approximation that obeys this error. And we can use relative error to do this, which is typically what we do. And this algorithm, the number of terms in these is really small. It's significantly smaller than anything you could get with a Fourier series. It actually, you can prove that it produces a near optimal or optimal number of terms in the approximation for a given error. And you can, and furthermore, you can apply this type of function to, integrable singular functions, periodic, non-periodic functions, or oscillatory functions. So you can apply it to lots of things. So here are the basic steps of the algorithm. If we're given these samples, first of all, the number of samples needs to be odd. And the only reason it needs to be odd is because we're going to construct a Heinkel matrix out of these samples. And you construct it in this way as shown, and if you don't have an odd number, it doesn't work out. So the next step is that you're going to solve what's called a Kohn eigenvalue problem for this. You're going to solve a Kohn eigenvalue problem for this matrix. Kohn eigenvalue problem, it's similar to a normal eigenvalue problem, except for you have this complex conjugate on the other vector. So you can, so when we do examples with this, we use the SVD to solve this, and that's where the SVD that I mentioned came in earlier. Okay, so once we solve this problem, we want to obtain M, where M is the index of singular value that we choose, roots of a Kohn eigenvalue polynomial in a correct region. So what is a Kohn eigenvalue polynomial? So we solve this problem, and we select this Kohn eigenvalue, which is going to control our error, and we find an associated Kohn eigenvector. Okay? Now, the entries of this Kohn eigenvector are what we use to form this polynomial. And once we form this polynomial, we find the roots of this polynomial. And a lot of this work is based on finding exponential approximations that decay. So in other words, as the variable grows, you want your approximation to exponentially decay to 0 as you go towards infinity. So we usually want these roots inside the unit disk. So once we found these roots, then we can take our original data and then we do what you typically do in a linear system. We solve a Vandermonde least squares problem to find the weights, and after that we just adjust the roots to get it in the form of e raised to something, and we get our approximation. So this works pretty well, and let's take a look at an example. And this is an example from the paper that I was talking about. So let's say we have a Bessel function, J0 of 100 pi x on the interval 0 to 1. The red dots are the samples that I used, so this is obviously oversampled. When we actually do these problems, we look for an oversample. We use an oversampling factor, typically of 2. This is more, but it doesn't really matter here. Okay, and we go through what we were talking about, and we solve the nodes and solve for the nodes, and we solve for the weights. Okay, so these are the nodes that we get, and in this approximation, I chose to use 29 of them, and then 29 weights also. And this circle represents the circle is the unit circle. So what we see is all these are inside the unit circle, and they're approaching points that are close to 2 points on the unit circle, which makes sense if you think about it. We're approximating a Bessel function, and the farther you get away from the origin, the Bessel function looks more like a cosine. So you have that these points are accumulating towards points on the unit circle, but they never get there. You also notice is that since this is a real valued function, that we have symmetry about the real axis, and we have that in the weights also. Okay. Yes.
Is there some ordering attached to this? What are they called? Eigenvalues or something like that?
So when you say ordering, you mean
Any
ordering?
natural way to say this is the first, this is the second?
Yes, there is. So recall when I was saying that we solved this problem, and the Kohn eigenvalue that you select determines your error. Well, and also recall that when I was saying these nonlinear approximations, they decay exponentially with the number of terms you get. Well, what controls the number of terms in your approximation is the index of the singular value and the Kohn eigenvalue and Kohn eigenvector that you choose. So for example, if I chose an index, the 30th one, I would have 29 roots and 29 weights. So yeah, there is an ordering, and the ordering is that the higher in the index that you go of singular value and singular vector, the better the approximation that you're using, and the more terms that you use in your approximation. Right. Okay, so, and this is the error result of the quick approximation that's done in the paper. And so this is error in log scale, so this is in digits. So I had chosen the Kohn eigenvalue to be 3.27 times 10 to the negative 12. And using 29 nodes, this line represents that, and you can see that we can reproduce the sequence that we were initially put in with that error. But also remember too that we do this with decaying exponentials, so if we take this approximation for this and take the limit as x goes to infinity of the approximation, then it's going to go to 0. All right. So now I'm going to talk a little bit about the second form of nonlinear approximation that's done in our group, nonlinear inversion of a Fourier transform. So this was also introduced by Greg and Lucas, and they consider reconstructing a compactly supported function with singularities from two types of data. So we have values of its Fourier transform available only on a bounded interval, or a limited number of Fourier coefficients. And you can choose between these two. It just depends on how you want to do the problem. If you want to say, well, I have some function, and then outside this interval, it's just 0, you would use something like this. Whereas if you're saying, okay, I have some function and it has compact support, but it's periodically repeating itself, then you would use a version like this. And I'm going to talk just a little bit about both of these nonlinear approximations. Okay, so real quick, the type of, we can do these approximations with different kinds of singularities, so discontinuities, the function and its derivatives, or more generally just integrable singularities. However, in this approximation, we're not assuming that we know where the singularities are. And the idea behind this is that we're going to use the nonlinear approximation that we just learned, except for on these given Fourier data. And what's nice is that if we approximate these Fourier data with decaying exponentials, that's going to give us an approximation of a function in the space domain by a linear combination of rational functions. And using this method, this approximation is going to mitigate the Gibbs phenomena without using windows or filtering, because the data that we approximate in the Fourier domain, we're going to extrapolate those data. And so instead of brutally cutting off data or windowing data, we can just kind of let it go to 0 as the approximation goes to infinity, and do an analytic Fourier transform to recover the function. So there are a couple of advantages to this. So one of them is, as before, we can look and see and find the level of noise in our function through our nonlinear approximation, through the Kohn eigenvalue problem that we do. We can actually find the level of noise that's in the problem. and then choose which con eigenvectors and con eigenvalues we use to avoid that noise. Yes?
I'm sorry, I don't know one of the questions.
That's okay.
How do you know noise from your function?
Okay, so that's a very good question. So the type of noise that we've considered in this is uncorrelated white Gaussian noise. Now, if you're talking about some sort of
You don't have statistics, what kind of rate of Gaussian noise?
no, no. So okay, right? Okay. So the resulting representation is going to be compressed in the sense that we can represent this function with a very small number of rational functions. So here's how we formulate the problem. So let's say we're given a real value, we have a real valued function. So its Fourier data is going to have symmetry. And so we're only going to look at samples in the positive direction. So given these input samples, once again we need an odd number and some length of our interval. And we're going to say that we assume that it sufficiently oversamples the Fourier transform. And on this interval, we construct a linear combination of decaying exponentials, just like we did before, where we obey an error and have a near optimal or minimal number of terms. So that's the first step of this approximation. The first step of this approximation is the last approximation that we did. Okay, and once again, just a reminder, both of these are complex valued, so the weights and the exponents are complex valued. The error depends on the number of initial samples and the length of your interval. And we have that we're working with decaying exponentials. So in such a case, we can extrapolate and then obtain our function from our approximation g hat through a Fourier transform. So we're given, sorry, my pointer is dying here. So we're given the inverse Fourier transform and our approximation. And once again, we said it was real valued. And since these are exponentials, we know how to analytically evaluate this transform, right? So we get a linear combination of rational functions. And these rational functions have a few properties. Okay. The function g is defined by 2m poles and the corresponding residues. 2m because this is the real part. G is real valued, and thus all of the poles are going to appear in terms of their complex conjugates. And like we saw in the first approximation, and it's a consequence of the optimality of these approximations, the poles that we're going to be looking at in the complex plane, if you have a function that has singularities, these poles will accumulate as they approach the singularities on the real line. And I'll show you guys an example of this right now. Okay, here's an example. So this is a compactly supported function with singularities of different kinds. We have jump in the zeroth, first order derivatives, etc., etc. And these are values of the Fourier transform. And these values decay down to a size of 1.2 times 10 to the negative 2. So if we were just to try and use a Fourier type approach to reconstruct this function, we would have significant Gibbs phenomena. We have significant oscillations near the singularities. And whereas a typical approach would be to apply some sort of window to this, where we either have a flat window for a while and then try to kill off the values at the end of the Fourier data, or we just start with something like a Kaiser window that just comes down and alters your data significantly. And we're going to look at the comparison between what happens when you use these windows versus what happens when you use the nonlinear approximations. All right, so these are the two windows that we're looking at. We're using just a Kaiser window and a flat window, a window that's flat up here for a while and then comes down and kills the function. And when you look at the reconstructions that you get from these three techniques, this is the Kaiser window up here, this is the flat window, and this is the rational approximation. So the first thing you see is that with the Kaiser window, you're causing a lot of damage in the approximation away from the singularity points, okay? So this is a significant error you have in here. Whereas if you use a flat window, you're going to do better away from the singularities, but closer to the singularities, you're going to have problems that go out for a significant amount of support, if you will. Whereas if you use a rational approximation, you have an error whose behavior looks like this, but instead the amount of damage, the amount of error that you're doing near the discontinuities is the support of it is shrunk down quite a bit. So it's not the errors that you incur from right here are not going into this area as much. Errors you incur from right here are not going to this area as much as with a windowed inversion or with a flat window, or if you're using a Kaiser window where it just causes a lot of damage all over the place. Okay, so, well, what happens if you do something with noise? So we're going to look at the same example, but we're going to add some independent Gaussian noise to it. And this is what I was talking about earlier about the about nonlinear approximations and being able to find out what your noise level is. So these are the first 28 singular values of the Hankel matrix that we construct without noise versus the first 28 that we have with noise. And so you see a significant flattening out of your data around where the noise level is. So the idea behind this is that you can choose a point that's above this threshold, and then you can apply your nonlinear techniques there. Now, something else I wanted to say about this. Okay. Well, we will continue on. Oh yes. Okay. Now I remember what. Sorry about that. The reason for this is that the type of noise that we're adding to this model, just the type of this noise, it's not well represented by linear combinations of exponentials with complex valued exponents. So that's why you start seeing a change in this behavior from this exponential decay in your singular values to this flattening out. So this is why you can say, oh, this is noise, whereas over here you don't have such a thing. All right, so here's the example with noise. So we didn't include the Kaiser window because it was doing a lot of damage outside of the singularity points anyways. And what you can see is that you get error that's pretty close to around the noise level away from the singularities. But once again, if you look at the singularities, the rational approximation, it doesn't do as good of a job beforehand when there was no noise added. But it still does a pretty good job and still does quite a bit better than the windowed version. Yes?
So this is
sorry.
on the previous slide. You use the same number of terms for your approximation for both pictures, so how you compare them?
For this picture and for this picture. Oh, this one we're just applying a window and then inverting with Fourier techniques, whereas this one is actually using a rational approximation.
Well, if you just do discrete Fourier transform, it's totally reversible. You will get one-to-one kind of
Well, yeah, but that's what you do, right? Is that you're applying a window and then you do an inverse.
Without any window, it's totally reversible.
Yes.
So if you apply direction and inverse Fourier transform.
Yes, yeah. It's a unitary. Yes.
With ones on diagonal, nothing happens. You have no error. So
Well,
you will have enormous error in the singularity.
no, if I have given, well. Okay.
Well,
Look, it's important. You
okay.
truncated your Fourier series.
No, nothing. Nobody truncates nothing. I just do discrete Fourier transform.
You're saying you're just given something. You're just given something. You FFT it, and then you inverse FFT it, and then you get the exact same thing. Sure, but yeah, that's exactly right. But what does that mean?
Problem that you have.
What does that mean, though?
Your data is not going to zero. If you try to do discrete Fourier transform, you will get a picture with a very significant oscillation, much worse than on the top picture.
Not unless I truncate it. That's what I'm asking. Is it truncated?
Good question. I think the real question is are you truncating, and so that you're really storing the same number of literally bits of information before you inverse transform?
Well, what we're saying is that you're given Fourier data. That's what you start with on an interval, and now you say, okay, well, I have a few options. I can either apply a window, and then apply an inverse Fourier transform, or I can just truncate it, and then go straight back. Well, the thing is we're not saying you're given something, take an FFT, do this, come back. That's not what we're saying. Our starting point here is the Fourier data, actually. We're not saying about how it got there at all. What we're saying is about how you can go back in a manner where you minimize problems like this. But I mean, you're perfectly right. It's unitary transformation. If you have something, you FFT it back, you're going to get exactly the same thing. But that's not what we're doing.
This is not the issue.
Yeah.
You are given a slowly decaying Fourier series. You take first 200 coefficients. They didn't decay to zero. Out of 2 million or whatever. Okay? You take 200 of them. You do inverse Fourier transform as you propose. You will have enormous oscillation.
Well, that's what I'm asking. How truncated are these things? Are they truncated the same way? Can we compare them?
Both pictures are obtained from 200 samples of the Fourier transform. That's all.
Now, if you have only Fourier transform, you don't have your function. There is nothing to compare it to.
Well,
Because you're
we're doing.
Let me
Okay.
reiterate. You have, this is an example, so you know the function. You can compute its Fourier transform exactly. You then sample it. You take first 200 samples. Everything else is totally random. From these 200 samples, if you do FFT or DFT, you will get Gibbs phenomenon. Typically, engineers put a window. Either the one that, well, there were two pictures of it. You reduce Gibbs phenomena by doing it. Okay? That's natural way of doing it, right?
Traditional, I would say. I'm not sure natural would work, but
Well, what else would you do?
I don't know. That's what people do in chemistry.
Right, so, and alternative to this is to do what he's describing.
So in all these cases, you're essentially coding with the same number of terms.
Of course.
Mhm.
No, I mean, that's what I was asking. Does it look like you still have Gibbs phenomenon? If you look at your error, it's still where your jump is. And it's not getting any smaller, it just gets narrower. And that's
Well,
exactly
but
when you do Fourier transform with increasing number of components.
but you're never going to just beat the Gibbs phenomena and just say, okay, it's gone. That's how we hold on a second, but that's how we minimize it, right? Is that we have the Gibbs phenomena near a discontinuity, and once we use this procedure where we extrapolate, what you're going to see is the Gibbs phenomena, it's going to squish together.
That's what I see on those pictures. That's
Yeah.
what, the expression. Do you use the same number of Fourier components or whatever components to show this picture? If
Well-
the same number, then it's impressive. If it's not, then I can do it with just increase Fourier transform. It will be the same Gibbs phenomena.
Okay, but that's the thing though, is that instead of we're not using a larger number of Fourier coefficients. What we're using a smaller number of rational functions. So the number is smaller, and you still get something better than if you just used a window.
Well, depends on your norm.
Right over here.
In infinite domain.
Well, yeah, okay. All right. So here's what I was mentioning about the poles. So this is the original function that we have. And these poles, these are the poles of our approximation just in the lower half space. And what we see is that these poles are accumulating towards our singularities of our function. So that's what I had already mentioned to you guys before. Real quick, here's an example of the same thing, but instead using a Fourier series. So this is our function that we're looking at, and it has discontinuities right here and discontinuities right here. And if you look at the poles are once again accumulating towards the, sorry about that, accumulating towards the discontinuities that we have in our function. And if we look at the error of the rational approximation that we do, if we use 63 of the Fourier coefficients and then do the approximation on those 63, this is the error that we're going to get, versus if we use 127 and then do our extrapolation procedure, we can get a much better error. Now, what's really interesting about this is look at the, if you look at the error away from these singularities that we encounter, you have a nice uniform error, and that's the, and there are a few reasons for that. If we, you can talk to me afterwards if you're interested in that. But so that's the same thing, but if you're doing it with Fourier series coefficients. So briefly, I would like to talk a little bit about using these methods to approximate data on a disk. And it's not really an extension of these methods, it's just an application. And this application, it's based on the nonlinear inversion for Fourier transforms on the real line. And the idea is, well, we have data on a disk, and we're going to do two approximations in two directions. One of them is in the angular direction, and the other one is in the radial direction. Now, what causes Gibbs phenomena is, the decay as you go off in the radial direction. So we're going to use exponentials on that part, and on the part where we are approximating an angle, we're going to use something else, just a standard linear approximation. Okay, so we're given data on a polar grid, or it's a nice equispaced polar grid. And what I want to start off doing is, if we're given this polar grid which has concentric circles on it, on each concentric circle I want to make an approximation with periodized B-splines. Now, there's a very good reason that I want to use periodized B-splines versus Fourier series coefficients. And that is just because I want some sort of localized extension versus extending the data in all directions at once. And I can explain it a little later. We approximate the B-spline coefficients via linear combinations of decaying exponentials, and such as this, where C is our original band limit, and I dropped the negative sign in this case just because it's easier. So what we're doing is that we're extending in the same way, but what we're extending are B-spline coefficients. So let's say we want to extrapolate outside of some original disk. What we do is we have an initial disk of data, we approximate all of those concentric circles, and then we do approximation on the B-spline coefficients via decaying exponentials. We choose some radius that we want to evaluate it at, and then we have a whole bunch of B-spline coefficients that we can evaluate the new function on that circle. And we're going to build up a grid in the 2D Fourier space in this approach.
Right?
Yes, absolutely.
Decaying exponentials, that kind of imposes some restriction on decay of the function.
So
inside of your disk, it doesn't have to decay really.
Okay. So this is the important thing. The reason that we want it to decay is because once we're extrapolating, the whole idea of the problem with Fourier analysis when you have Fourier data that doesn't sufficiently decay is you get Gibbs phenomena. So if you approximate in your disk by decaying exponentials and then extrapolate outside of that disk, you're going to have exponential decay outside of that disk.
Which is not physically justified by any means. Your function doesn't have to be the thing also. I think about phase errors and optics incidentally.
Well, I mean, it is going to decay, but now the question is your window physically justified? Does it have to decay that much faster? I mean, if you use something like a window, it's going to decay really quickly, or if you truncate, it's going to chop off. That's certainly not physically justified. So, I mean, these things where you're giving it exponential decay, I mean, sure, maybe it had algebraic decay outside of that interval, but you're still doing something that's much more benign, much more mild than applying a very harsh window or just directly truncating it. And that's kind of the whole idea of what we're doing. Okay, so as I was saying, the next step is we want to extrapolate the coefficients, and once we've extrapolated the B-spline coefficients, there are two methods for inverting the Fourier data. So the first one is, okay, we're going to evaluate a radial integral first in the inverse 2D Fourier transform. And this method is similar to a filtered back projection. Whereas we could say, all right, well, instead, we just want to extrapolate to a very large grid, whether it's a polar grid or a Cartesian grid, and then we're going to invert either using the unequally spaced fast Fourier transform or a 2D inverse fast Fourier transform. Okay, so the filtered back projection method. So this is the approximation that we build up once we have the B-splines and the decaying exponentials. And this is the inverse Fourier integral that we want to do. So what we're going to do in this method is that since these are exponentials and this goes off to infinity, we can evaluate this integral analytically. And evaluating this integral gives us this integral. Now, a few things about this integral. There aren't any poles on the unit circle. No discontinuities on the unit circle you'd have to worry about, so that's nice. This is going to reduce the Gibbs phenomenon the way that we've discussed a few times already, so that we've integrated off towards infinity. But you have to be careful doing this integral. And the reason you have to be careful is that the integrand can have some very sharp peaks. And these sharp peaks mean that you can't just discretize it using the trapezoidal rule necessarily efficiently. You might have to use a lot of samples. But nevertheless, we have a very basic example that we want to do. So the basic example is an elliptical circ function, and it has a semi-major axis of 1, semi-minor axis of 9/10. So we sample this on the Fourier domain, and the absolute value decays to 7.2 times 10 to the negative fourth, and that's the singular value that we choose. So our result, this is what our result's going to look like, but we can't really tell that much from it. So let's look at a couple of cross sections. So if we look at the cross section around the semi-minor axis, our approximation is flat away from the singularity, and you have the error next to the singularity, which is what you expect. And you have the same phenomena with the semi-minor axis. You have the Gibbs phenomena is squished into the samples here, if you will. So the actual error kind of peaks up here like this, but it's still quite thin, just like all the other examples we've shown you. But the difference is that this is in every direction on the Fourier domain. Okay, and I briefly want to go over the other version where we have this approximation, and instead of evaluating the radial integral analytically, we just want to resample our approximation. And we choose a new band limit such that we mitigate the Gibbs phenomena in our result. And if we use the unequally spaced FFT, I just wanted to briefly mention that the quadrature nodes that we would use in weights were defined in this paper. However, in the example that I did, I just extrapolated to a Cartesian grid and did an inverse 2D FFT. So this outlines the circ that we looked at in this example, and these are the data that we used. It decayed to 3.7 times 10 to the negative 3, and I chose a singular value that's slightly smaller than that. And we extend the original band limit by a factor of 5. So instead of evaluating an interval that goes off to infinity, all that we've done is said, okay, we're going to just make this disk's radius increase by a factor of 5. So looking at a cross-section of the circ, this is what we would get if we just interpolated to a grid and then applied an inverse 2D FFT. So this is what we were talking about, but it's just but this applies in each direction. Whereas if we extend the error by a factor of, we extend the support by a factor of 5, we see these oscillations get squished in next to the singularity. And if you look at the error, for this, we have, this is around to where our Fourier data decayed, and this is the reconstruction with extension. So you see that the larger errors are nicely localized to our discontinuities. Whereas if you look at the reconstruction without extension, we have practically all of this above that same level that we were looking at right here. So this is just an easy way to extend this to the disk. And that is all I had for you guys. Here are the three papers that I referenced quite a bit. So please take a look at them, and thank you very much for your attention.
We have time for questions.
Rob.
I have a question as to what would happen if you wanted to approximate real-world data that does not decay exponentially in the radial direction in a 2D context or in a 1D context in some particular direction.
Okay. So that's actually something that I'm going to be trying to do in my thesis. I'm going to be applying these techniques to electron microscopy and X-ray tomography type problems where I do exactly that. So I guess the cop-out answer is I'll tell you in a little bit. But so the idea though is that what we're approximating in the Fourier domain doesn't have exponential decay though. That's not a requirement. What we are going to do is if we're given data in the Fourier domain within an interval, we want to approximate those data with decaying exponentials such that we do a very good job inside that interval. But since we use decaying exponentials, outside it's going to have exponential decay. So if you ask what's going to happen when you do that, it's going to do something where you're going to get much less harsh effects than like a window would give you, or something like that. Which is something that engineers use on real-world type issues. But so you'll get some of the same effects, but it'll be less drastic.
Let me ask a following question.
Yeah.
You're approximating in this nonlinear way or as a sum of complex exponentials, which means in the Fourier domain you have rational functions.
Yeah. Well, most of the time we use it in the reverse way.
That doesn't really matter.
Fair enough.
The point is that there's a real tension between the use of these particular complex exponentials as basis functions from the point of view of extrapolation and their usefulness as regards removal or easing problems of Gibbs phenomena.
Mm-hmm. Well, so, okay, hold on a second though. But so the key word that you're using is basis functions. We're not using basis functions, though. I mean, we're using functions that we choose from sets that are larger than basis functions. So we don't have stuff like countability, stuff, them spanning a subspace, stuff like that. We're,
You might be able to restrict somehow. For example, even if you're using temporal exponentials,
So-
that's the case when you don't allow them to decay at all.
So I'm sorry. So when you say using complex exponentials, what are you talking about in the exponents? Are you talking about if they're purely complex valued, so like something like a Fourier basis, or are you talking about, okay, well, see, that's something that we don't do. So what we're doing instead is that most of the time with a Fourier basis, the exponentials live on the unit circle, right? They have magnitude 1. One of the nice things about this approximation is that we're not restricting these things to have magnitude 1. They can jump inside, outside the unit circle. That's something that they're allowed to do. Now, so that can give you problems if you're trying to approximate some data that doesn't have some sort of decay behavior within the interval. That can give you problems. But in the applications where we're using decaying exponentials, we're trying to approximate within exponentials things that decay within an interval, and then so we'll get exponentials that are inside the unit circle.
So you do actually allow for the possibility that it could be outside. So
Mm-hmm.
your optimization process might naturally lead to.
Yeah. Oh, sorry. Go ahead, Greg.
You can get nodes outside, but then you cannot extend because then it will grow.
Then it just blows up.
It blows up. Fortunately, natural functions that we use, let's say, the worst case would be jump or individual singularity. They all have decaying Fourier transforms. Now, if you don't have enough data, you may have this phenomenon of finding spurious nodes outside. But if you have enough data, then you'll be fine. So the fair comparison here, what else would you do? You say if you've given only unlimited piece of the function, what are your choices? You can put a window, you can play with some other games, but you have to do something, right? You cannot just if your Fourier transform didn't come to 0, you have to do something. Right? You force it by windows, or you do this. And the other question was why using exponentials? Well, ideally you can try to use other functions, but you need algorithms. You need to be able to compute. So this is the case when you can compute. So there were attempts to do this using inverse polynomial type decay because it's sort of more corresponds to the nature of the singularities and so on. But then you cannot solve.
You mean analytically?
Well, analytically, numerically, you get awful systems that very difficult to solve, and you're not guaranteed to find the solution. The part that is important here is that the original nonlinear problem is reduced to nonlinear problems which you know more or less how to solve, like eigenvalue problems and finding roots. Finding roots is the worst part of it.
Any other question or comment?
Maybe I missed something, but it looks like you showed us some recipe. Do this with your data, make Hankel matrix, solve some weird eigenvalue problem, plug it over in, and you showed a couple examples that it actually works. Is there some kind of general theory behind it that will tell us, when it works, when it doesn't, what to expect?
Yeah, and there is a general theory that is involved behind it. Yeah, and I didn't present any of it here today. I didn't go through and improve the algorithm, stuff like that. But you can look in these papers and find more of those details. Absolutely.
I'm not talking about algorithms. There's some facts that you can approximate the function with. That's the best way to approximate a function is to do Well, following your recipe book, not anything else. Can you prove it actually?
Well, you can, well, yeah, you can. There's the work of, I'm sorry, Greg, I'm gonna slaughter their names. Adamian, Arav, and Crane. They've put in a lot of work on approximating functions with things on the unit circle with rational functions with poles inside, and a lot of this work corresponds to and is based off of that work that was done by them in the late 60s. So yes, you can prove a lot of this stuff.
So let me give more details. So there were papers by Araf, Adamian, and Crane, late 60s and 70s, which dealt with a slightly different problem, where basically you were not given data on finite interval, it was infinite interval, and they have a complete theory, and this theory actually is a foundation of H infinity control. So that's what, when you hear H infinity control theory, that's based on it. What we did with Lucas is do it on a finite interval. And there are still missing pieces and proofs, but basically the theory is there. And it's clearly there when, if you do it a posteriori, that is, if you can extend to infinite interval, then the other theory takes over and justifies all these things that you mentioned. If it doesn't extend, then it doesn't justify. So it's a little bit like that.
Are there references in these references?
Yeah.
Mm-hmm.
So let's then we get again